Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 7th, 2026, just yesterday. It introduces CHORD, a universal generative pipeline that synthesizes complex 4D scene dynamics by distilling motion information from 2D video models, achieving over 87% user preference for motion realism. The paper is titled Choreographing a World of Dynamic Objects, and as we'll see later, the resulting physical accuracy is significant enough to even enable zero-shot robotic manipulation tasks. Figure 1 illustrates the diverse range of 4D dynamics that the CHORD pipeline can synthesize. The top row demonstrates complex human-object interactions, such as a man placing a plate into a microwave. In the middle row, on the left, we see realistic soft-body deformation, where a cushion compresses under a cat's steps. Finally, the bottom right captures multi-body physics, showing a child jumping on a seesaw to launch a brick into the air, which proves the system isn't limited to just one type of motion. Figure 3 details the hierarchical control point representation that makes these complex motions possible. To stabilize the optimization, the method splits deformation into two spatial levels. On the left, spanning the initial and deformed states, we see coarse control points, shown as blue blobs, which manage large-scale movements like the arm's trajectory. Then, the inset on the right reveals the fine control points. These smaller red markers focus on local details, such as the articulation of fingers, ensuring the model captures both the broad stroke of the action and the subtle nuances. Alright, Figure 2 brings these pieces together into the complete workflow. On the left, the process begins by taking static input meshes and converting them into 3D Gaussian splatting representations, which allows the system to compute smooth gradients. Moving to the center, this initializes the 4D representation, where the model iteratively renders video clips of the scene in motion. To guide this learning, the right side shows how these clips pass through a pre-trained video generation model, which acts as a teacher by sending feedback gradients back to refine the trajectory. Simultaneously, the pink box at the top applies spatial and temporal smoothness regularization, ensuring the resulting animation remains physically coherent. Well, just as Figure 3 managed spatial detail, Figure 4 addresses temporal consistency using a Fenwick tree. This hierarchical structure, shown by the stacked blue blocks, stores motion parameters across overlapping time intervals, rather than for single frames in isolation. On the right, the diagram demonstrates how the specific pose for frame 6 is constructed by querying a combination of these shared nodes. This approach naturally enforces smoothness, because nearby frames are built from the same underlying trajectory components. So Table 1 validates this pipeline by comparing CHORD against 5 baselines. The user study columns on the left show a massive performance gap between the methods. While the best competitor, Trajectory Crafter, struggles to break 10%, CHORD captures nearly 88% of user preference for both alignment and realism. On the right, the automated Video-Fi2 scores confirm this trend, with CHORD leading in semantic adherence. It falls slightly behind in physical common sense, but only because the top baseline often defaults to static objects, which are stable but unresponsive. While Table 1 quantified the lead, Figure 5 visualizes why the gap is so large through qualitative comparisons. The layout displays the initial input on the left, followed by 4 baseline methods, and finally the CHORD results on the far right. In the top row, which depicts a cat stepping on a cushion, previous methods like Motion Dreamer suffer from severe distortion or simply slide the object without interaction. In contrast, the CHORD columns show the cat naturally lifting its legs and the cushion compressing under its paws. We see this physics awareness again in the bottom row, where the model correctly captures the elastic deformation of a trampoline as a block falls onto it. Wrapping up, CHORD demonstrates that distilling 2D video priors is a viable path to creating physically grounded 3D dynamics. By avoiding category-specific heuristics, it paves the way for more robust world models in robotics and embodied AI. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.